Hey everyone, and welcome to another LeetCode problem. So today we're going to be doing problem number 2713, maximum strictly increasing cells in a matrix. And this problem is from the last LeetCode challenge, and it was a 6-point problem on there. And honestly, I had to look at this problem for a while, and I had to read in the submissions, but a lot of the submissions are quite difficult to understand, so I had to kind of, read the submissions, figure it out, and then get a good sense of what they're trying to do in the problem. But now that I have seen this problem, I think I can definitely understand it pretty well, and I am going to try to explain it as best as I can. So we're given a one-indexed m by n integer matrix mat. You can select any cell in the matrix as your starting cell. And from the starting cell, you can move to any other cell in the same row or column, but only if the value is strictly greater than the value in the current cell. You can repeat this as many times as possible, moving from cell to cell, until you can no longer make any moves, and your task is to find the maximum number of cells that you can visit in the matrix. So there's a couple of things about this problem. There are other problems on LeetCode that have some constraints that make it a lot easier. So some problems let you move only one space, so like one left, one right, and so on. And it is same thing, strictly increasing. So that's the first thing you're going to want to figure out is, I originally looked at this problem and I was like, oh, it's super easy. All you can move is one space. Okay. It's just, and by the way, so you're going to have to know dynamic programming from this problem to begin to understand what to do, because there is an optimization of dynamic programming. So if you don't know dynamic programming, I'd recommend looking at some of my other videos on that, or just look up a bottom-up dynamic programming video. But the intuition for this problem, so let's just take a look here, right? Let's just look at this first one. And then we're going to look at some bigger ones and understand. So for one thing, you can move as many squares as you want in the same row or column. So let's actually look at this, instead of this one, let's look at this bigger one. So let's look at this one, 3, 1, 5. And let's just figure out like what a solution would look like, would it work, and how to optimize. So a simple solution that you can think of is, let's just think top down for now. Let's just think of a memoization problem where we have a visited. So we have this visited as always, right, for every single row and column. And all we do is, for every cell, we just do 1 plus the maximum of, we try to visit every single other cell. Right, so let's say we start at, and then we're gonna loop through every single cell in this matrix. So we're gonna have a for, row and row for column and columns, and we're gonna try to loop through every single cell of these as the starting cell. And then we are going to try to visit every other cell, and because we're recording them in our visited, then what is going to be our space and time complexity for something like that? Right? Just a basic dynamic programming memoization where we start at one thing, we loop through every single other thing in its row. So right, so we loop through these two, we loop through whatever's down here, and then we get the maximum. And then we're not going to be doing repeated work because, remember, anytime we start at some location, it doesn't matter how we got here for the solution, right? So if we start here, it doesn't matter that we got here from -9 or whatever, because we're only going to strictly increasing cells, so you don't have to have some kind of, did we come from here or not? It doesn't matter. These are all independent, so you can do dynamic programming. And the complexity of such a solution would be, let's say, so what is this? It's an m by n matrix. So remember what we're doing, right? So we are looping through this entire thing, and we are starting at every single cell. So that's going to be n by n, right? We're starting at every matrix, or every cell. Then we do have a for loop that we iterate through the rows and columns. But the thing about this is, because most of these values are going to be stored, we're actually only calculating the value in one specific square one time. So actually our solution would be this, because this is a simple dynamic programming where you just save where you're at, and you can code that up if you want. But the problem is, once again, I say this a lot in a lot of my videos, is take a look at the constraints, and then from the constraints you'll kind of know if that'll fail. Also, I mean, hint hint, I guess if you're given a difficulty 6 hard problem on a LeetCode contest, it's not going to be as simple as just a standard dynamic program, because that's something you can code up if you do a lot of dynamic programming in like 5 minutes. And yeah, so the constraints are 10 to the 5th. So it's going to be 10 to the 5th times 10 to the 5th, which is quadratic, which is not going to pass. So then we have to figure out what optimizations can we make. And I do think it's really hard to figure out what optimizations we can make to this unless you actually look at the bottom-up programming solution for this. So let's take a look at that and let's ask ourselves some questions. So let's say we have these numbers again. Okay. And so what would the dynamic programming first of all look like, right? So the way dynamic programming works is you're going to have something, you're going to have a base case. And then from there, you use that base case to calculate everything else. And so let's take a look at these things on the left. Well, what's the base case? What can we use to know right away what would be the answer? Well, so let's see what the question's asking again, right? So it's asking to move, we can move to a strictly greater cell until we can't make any moves. So what if we take all these cells, so we just have something like, let's just say value, row column, we take all of these cells, we put them into an array, right? So this would be, 0, 0, and then the value would be 3 and so on. So 3, 0, 0, and we sort them. And we sort them in reverse, so we get the biggest value first. Well, the biggest value here is going to be this value here, right? So it's going to be 7, and then the row is going to be 2, and column's going to be 2, right? No, row is going to be 1, sorry. Okay, so now we sort them, and then when we take the if we do these in sorted order, where we start with the biggest value, well, when we're here, and let's say the other thing we do, so let's say we make this new matrix and we initialize all these things with zeros. Okay? It's going to be the same size as this. Now, what we can do is we can go down our sorted list of these, right? And so the first one is going to be this 7, 1, 2, and we could say, okay, we're at 7, 1, 2. Well, first of all, intuitively, what would be the result here? What would be the result? So we know that we've started at the biggest value. Well, we can't travel anywhere else, right? So if we get a 1 point for simply starting there, then our value is going to be 1. But we can't go anywhere else, right? We know because that's our biggest value. And so because this is sorted, now let's take our second biggest value. So our second biggest value is actually up here. And all we have to do, if you notice, is wherever we're at, so let's say we're at some index, what we have to do is we can just take the maximum of the row and the column, right? So the maximum of this row and this column right now, before we put in the 6 value, so we put in the 7, right? Let's just say that. We're at the 6, and that's going to be at this location. So the maximum is going to be 1, and then we add 1 because we are here, right? So we can go 1, so that's going to be 2. Okay, what's our next value? It's 5. 5 is down here. And we do the same thing. So we say, okay, what's the maximum of the row? And what's the maximum of the column? And then we add 1. So that's going to be 2, right? Because the maximum is 1. Okay, now we have a 3. The maximum of the row and the column is going to be 2. We add 1, so that's going to be 3. Then we have value 1, so that's going to be 4. Maximum was 3. Then we have value -9. And here it is 4. And that's the solution, right? So we can start at this -9, we can go up here, then we can go to 6, we can go to 7. And the other place is 4 as well, so you can see we can start at this 1 as well, and we should have some solution. So let's see what that looks like. Well, we can start at 1, we can go to 3, then we can go to 6, then we can go to 7. So either of these work. So now we know that how to get this. And I'm going to get rid of all this stuff, and let's just say we have this again, right? So let me actually, let's do this actually. Let's do this. Let's select this area, and let's just do this. Now that we know how to get this, what would be the time and space complexity of a solution like this? Well, for every single node, right? So there's m by n nodes. For every single node, we'd have to check the row and the column. And so we still have the problem of for every single node we have to check the row and the column. So that would be the row is, let's say, m, and the column is n. So we still have this problem where we have to check the whole row and the whole column. Or actually, I think that would be m by n times m plus n. So it's not quite. So it's still not great, right? Because for every single one of these, we still have to do this m plus n, where we check the row and the column. It's still not ideal. I think before we had a worse solution, but Actually, no, no, never mind. Sorry, we didn't have a worse solution. So right now, this is the same complexity as top-down, but at least we're understanding kind of what we're doing. And so let's think of optimizations we can make. Well, let's go back and let's figure something out. So let's actually get rid of this and let's go through this one more time, but we're going to try to notice something. So let's go through this exact same thing, and then we're going to try to notice something. So we're going to start the same thing. We're going to start at the same exact number, right? We're going to start at the 7. And these are all going to be 0. And what we did before was we said we need to get the maximum of the row, right? Well, what if instead of doing that, what if instead of looking through this whole row, we actually store these maximums somewhere else? So let's see what that would look like, right? So we have these maximums and we store, let's say we store max row, maybe. And we initialize them all to 0 as well. So how many rows are there? There are 2, so it's going to be 0, 0. And then max column. And there are 3 columns. So now really, by the way, when we are, instead of these values, we're going to actually be updating these max row and max column values. So even though we are still going to be going in this order, that's what it's going to look like. And so let's try 7. So 7 is row 1, column 2. And so this, let's just put the indices here. It says 0, 1, 0, 1, 2, right? So we're going to take the max row that shares the row with 7 and get the value there at the right index. So it's going to be index 0. And then it's going to be here, we are going to be at column 2. So we're going to say 0, 0 plus 1. Okay, make that 1. And then whenever we get a value, we're guaranteed to have the max value at that index, right? Because we're taking the max values at this index, and then we're adding 1. So we're guaranteed to have them higher. So now what we can do is we can actually update these max row and max column. So because 7 has a max row of 1, we can update that to 1, and max column of 2, we can update that to 1. And so let's actually delete this little grid. We don't even need it anymore. And let's just put these max row and max columns up here. So we put in 7, then we're out of that. So let's just say max row is R, and the values after putting in 7 are 0 and 1. And then for column, they are 0, 0, and 1. Okay, now we try to put in 6, right? So for 6, it's going to be 6. Then the row for 6 is going to be 0, column 2. So 0, column 2. Okay, that's 1. So now we add 1, so that's going to be 2. And then it's this value and this value. So now we update it. So 2, 1. Update it. So let's delete this. And let's update it to a 1. And you can see kind of how we do this. So we would just basically get the biggest value in linear time, because we're going to store these biggest values, and we can keep going, right? So then we'd get a 5, and then the row is 1, and the column is 1, so it would be 1, 1, it would be 1, then we would be 2, so we'd update this to 1. Sorry, we'd update this to 2, right? Because the biggest value would be 2. We update this to 2, and so on. And then at the end, we're going to have some values, right? So we're going to have these max row and max column values. And it's pretty simple what we do after that. So what we do after that is we have, like, let's say we have these row and column values. Let's just say they're like this at the end, once we go through every single thing. Let's say they are like 1, 2, 3. Now simply we can just take the biggest value in anything here, and that's going to be our output. But there is one edge case that we have to think about, and I'm going to show that as well. And I can even show that with this original dynamic programming solution, and then I can kind of explain what would happen. So let's say we have something like this. We're going to make a new original matrix instead of this 316, 957. Let's say we do 316, 7, and then we have something like 5, 5. Right? So we have equal values. So now what would that look like for, and we're just going to use this non-optimized, but then you're going to see the problem. So or sorry, actually, let's do this with the optimized row and column, right? So let's do this with the optimized. So we're gonna have the row column. We're gonna have two rows, so they're gonna be 0, 0, and then we're gonna have columns. We're gonna have 0, 0, 0, and let's just go through these numbers, and then we're gonna see the problem. Okay, so 7 is that, and let's just label these. So this is row 0 or 1, row 0, 1, 2. Okay, so 7 is at row 1, column 2. Okay, so row 1 here, or sorry, row 1 here, column 2, and then we are going to update its value to 1, and so we're going to take these, update its value to 1. Okay, we got rid of the 7. Now 6 is at row 0, column 2. Okay, so that's going to be here. So it's going to have a value of 2, right? Because this is 0, 1, so it's going to take the biggest. It'll be 1. It'll update it to 2. Then we're going to update this to 2, and we're going to update this to 2. Okay, so now let's go to 5. Let's go to this 5 actually. So it's going to be row 1, column 1. So row 1, column 1. That's going to be 1. We're going to add another one, so that's going to be 2. So 2, 2. So does that seem right so far, right? So let's say we're at this 5. It's saying the most we can travel is 2. Well, that's right? We can go 5, and then we go to 7. So that would be 2. Okay, now let's go to this 5 right here. So that's at row 1, column 0. So row 1 is here, column 0 is here, so it's 2, 0, so it would be 2 plus 1, it would be 3. So now we update this, 3. And then this should be 3 as well. Well, now let's think about this. So with this 5, what's the most we can actually travel? Well, we start at this 5 and go to 7, so it's actually 2. So you see the problem that we are into, that when we have values that are the same, we are updating this row and this column after we go through the value, and then when we actually get the same value, even though it's not lower, we're treating it as if it's lower. Because for our previous stuff, we had the biggest number, then we had a smaller number, then we had a smaller number, and whatever. But if we just have a bunch of numbers that are the same, like let's take some extreme case, right? So let's just take a case like this, where we have something like this, and every single number is the same, right? So let's just say these are all 1. Well, now they're all the biggest number. And so we're gonna keep updating this, and we're gonna keep increasing our max row and max column every time. But we don't actually want to do that. What we want to do is we want to go through every single instance. So let me actually go back to that other example. We want to go through every single instance of the same number, and then we can update. So for example, if we know that, let me go back here. Yeah. What we need to actually do is we need to go through every single instance of this number, figure out what its value would be, using the previous stuff, and then store those somewhere. And then once we get to a new number, then we can go back to what we calculated for these numbers, and then we can actually change these row and column. Because if we're doing that one by one, then it doesn't make any sense, right? Because then the value for this was 3, and even though it should be 2. So what we should do is we should calculate the value for this, let's say it'd be 2. We should calculate the value for this, let's say it'd be 2. Then when we get to a smaller number, then we update these 2's into their corresponding row and column. And then we can simply do that by saying the value at the row, and so we just go through everything we went through again once we get to a new number, and we just say the value at whatever index this matches is the max of whatever it is now and this number. We are going to have to check for the max, because this number can be bigger than this or whatever. Like they can be different places, so these aren't always equal. So let's actually go through the code, and I'll try to explain all that. And so those are the basic. So those are the. Oh, and by the way, so if we have something like this, then what's our time complexity? So remember, we're actually sorting the numbers. So if it's m by n, then it would be m by n log m by n to sort. Right? Because it's n log n to sort some sequence, so it would be so this would be our time complexity. And then when we're actually getting this row and column and updating, this should all be constant time operations, because we're just saying, hey, we're at some index, give me the value in here that's at the same index. That's constant time, and then traversing through the array is going to be m by n. But because this is bigger, then that doesn't matter. So let's actually go through the code, and let's try to explain that. Okay, so we have this rows and columns, which is just the rows and the columns. Now this numbers is going to be the numbers that we are actually going to be storing, right? So like I said, we're going to be taking, so we loop through these rows and columns, and we just append the number, the row, and the column, and then we sort them. And then we're sorting them in reverse, right? So for our initial example of this 3, 1, 3, 4, it would be, you know, array would be 4, 1, 1, and so on, right? That would be row, column, value. So it's always value, row, column, sorted decreasing from the value. Okay. And so then we make these row counts and these column counts, which is our max row and max column in our previous example. And we set them equal to 0 because there's 0 at first. And then the other thing we do is we have this temp solutions array, and let me just show you why that would be. So let's say we have these numbers 4, 3, 3, 1. What I'm actually going to do is every time I get to a new number, I'm going to say, is this number different than the number before? And I'm going to initialize the number before to be like negative infinity or something. And if it is, then, and I'm also going to have an index of where was my last number that I was at. Right? So at first I'm going to initialize that to 0 as well, but I'll show you what that would look like in going through this. So at first we say, okay, is 4 different than a number 4? Yes, because we had something initialized. Then take everything that's in temp solutions and use that to update the rows and the columns. So for example, when we take this 4, we're not actually going to be updating the row counts and the column counts. We're simply going to calculate whatever this would be, whatever value this would be in the row and the column. We're going to put that in temp solutions. Let's call that T. We're going to append that in. Then when we go to 3, we're going to say, oh, is 3 different than our last number? Well, yeah, it is. It's different than the 4. So now we're going to need to go through every single number that was a 4, pop them from the temp solutions, and change the row and the column based on that. And then we're going to go, so we're going to go through this 3, then we're going to go to this 3, and we're going to say, is it different than the last number? No. So just keep adding to temp solutions. And then once we get to a new number, we pop from temp solutions. Also, once we get to a new number, we can just make this temp solutions empty. So this temp solutions is just going to store the values that we get for each integer until we get a new one. And then that way we can store them. And then once we get a new one, we can go through everything that we stored and we can update this. We can update the max row and max column accordingly, which would be these. And so that's what we're doing. So I said last number is floated infinite just so I get another number right away. And so the same thing that I was talking about, we have a number, we have a row and a column. When the last number is different, then I have to have some way to go through temp solutions. And because temp solutions is not going to have the same index as this numbers, I'm always making it 0. Sorry, I'm not always making it 0. I'm always making it empty. Then I just use this index to travel through temp solutions. So I just say, so I have this index of last num index, and it goes up to the current number that I'm at. And so pretty much if last num index, let's say was, let's say we're at some number like here. So this is what, 0, 1, 2, 3. So this is index 3. Last num index is 1. So it's going to be for I in range of 1 to 3, which is going to be 2 numbers. And then the index that I'm actually iterating is going to start at 0. And then so it's going to be T0, T1, and so on. And those are going to be the temp solutions. Okay. So that's what I'm doing here. I set an index equal to 0, and then I also remember for these row counts and these column counts, we take the maximum of whatever it is and whatever we stored every time. And then we just increment the index, and as soon as we went through our previous number, we make this temp solution 0, or we get rid of everything, and then we make the last num index the current number I'm at. So right here I'm at a new number, right? So because if this number is not the last number, then we're at a new number. So then I just change these values. Last num index is the number I'm at, and then last number is the current number I'm at. And then simply so this would be the other case. Like once we're actually done going through, we got to a new number. Now I make my temp solutions empty. Now I'm just going to be appending the value here, right? So remember, the value at some spot is the max of the row and the column plus 1. So we're just going to be appending that to temp solutions again, and then when we get a new number, we're going to be popping all those again. And so, and by the way, so the last thing is, so if we have these temp solutions, we are going to have some numbers, right, like this. And we are only changing the values of the max row and max column when we hit a new number, but for the very last iteration, we're going to go through some number at the end, and so temp solutions won't be empty. So after I'm done with this loop, I am going to have some stuff in the temp solutions that I need to still update the rows and the columns. So I'm just doing that at the very end of this for loop, where I'm just saying whatever's left in temp solutions, let's just update that. And then, like I said, at the very end, you just simply return the maximum of these row counts and column counts, and that's your answer. and so we can run that. My mic cut out there for a second. My battery dies a lot. So it's actually funny. When I ran this before, I think it was beating 100%. So I guess there's not that many accepted solutions. I think the reason it's also failing a lot, as you can see, its acceptance rate is 13%, is because everyone is just trying the memoization solution. And the memoization solution, you can code that up yourself if you want to start. And then, so what may be a good way to do if you really want to practice is code up the memoization solution with no optimization, then code up the bottom up like what I showed you with these zeros, right? So code this up, this should still fail, and then code up the optimizations, and that would probably help you understand it better. So let's actually, I'm curious, let's see if we can beat the 100 or it's just random, but yeah. Okay, now we're beating 100 again, so there's probably not too many submitted. Okay, and so the other thing we need to do is we need to figure out the time and space complexity, right? So time and space complexity, this sort, like I said, this sort, if this is m by n, to sort is, so if something is n long, to sort is n log n, right? And so if this is m by n long, then it's m by n times log n. And so that's going to be our sort, or m by n, yeah, let me show you. So m by n log m by n. And now, remember, this is just linear time, right? So this is just going to be m by n, which is shorter than this. And all of these changes should be linear time. We're just indexing directly and things like that. We're not doing anything in anything else. And space-time, so let's think about that. So space, we do have this. I think the longest thing we have is this array of all these values, which should be actually, sorry, so time. Okay, so space should be O of mn because the number of values is going to be m times n, and this shouldn't have a log or anything. So this numbers is going to be mn, this rows is going to be m, this is going to be n. Temp values also can never exceed the number of numbers because the most we can have is like if every single number is like a 3 or something, then temp values would store the entire list, but that wouldn't be bigger than this. Okay, so that's it for this problem, and I hope you liked it. These 6-star problems are definitely challenging and make you think outside the box, and it's kind of interesting to optimize something that you would think would be pretty optimized, like a bottom-up dynamic programming solution, but it's definitely interesting. So if you liked this video, please like and subscribe, and I'll see you in the next one.